Good morning, students. In the last class, we discussed a few problems based on the fringe width. So today, we shall continue few more problems which are asked in the previous year question paper. Right? Next, question number 4. Calculate the distance between the centers of fourth and seventh bright fringe. Fourth and seventh bright fringes in the interference pattern. In the interference pattern produced in Higgs double slit experiment. Given the separation between the slits is 1.1 millimeter. Wavelength of light used that is 589.3 nanometer. The distance of the screen from the slits is 1.3 meter, right? So here the question is given. So here they given the calculate the distance between the centers of the fourth and seventh bright fringe in the interference pattern produced in the Young's double slit experiment. Given the separation between the slits is 1.1 millimeter, wavelength of the light used, and distance of the screen from the slits is 1.3 meter. So here we have to find the distance between the centers of fourth and seventh, and one more is important is for the bright fringes. So here if we consider this one is the screen, right? So if it is the center, that is at home, it is always the bright fringe. So we have to calculate the given the distance x, that is fourth bright fringe. So here it is fourth bright fringe, then it becomes x4, right? Then seventh bright fringe. So after 4 we have seventh bright fringe. Somewhere here we have the distance x7 from the central bright fringe, that is x7. So we need to find out the distance between the x7 and the x4. That is, we have to find the distance between. So this one is the x7, that is seventh bright fringe, and here we have the fourth bright fringe. So we need to find the distance between these two bright fringes. So for that we have the relation for the bright fringe, that is the condition for the bright fringe, that is xn is equals to n lambda d divided by small d. So this is for the bright fringe. In the question also they mentioned the bright fringe, that's why we are taken. So this formula for the bright fringe xn, where n is the n position. If it is 1, then x1 is equals to, then n value becomes 1. Here in the question they given 4 and 7. Then for fourth bright fringe it becomes x4 is equals to 4 lambda d divided by d. Then for the seventh bright fringe it becomes x7 is equals to 7 lambda d divided by d. So we need to find the difference between these two bright fringes. That is, we need to find the difference x7 minus x4, that is equals to. So here we have x7 value is 7 lambda d divided by small d, minus we have fourth bright fringe, that is 4 lambda d divided by small d. So all these terms are same. Then we can subtract 7 minus 4, that is we get 3 lambda d divided by d. So this is the difference between the two bright fringes, that is x7 minus x4. Right, for the bright fringe we have xn is equals to n lambda d divided by d. So at any position from the central bright fringe we have xn is equals to n lambda d divided by d. So in the given only, in the question only they given the separation between the slits, that is small d they given, that is 1.1 millimeter, that is given separation between the slits, that is small d is equals to 1.1 millimeter. If you write means 1.1 into 10 to the power of minus 3 meter. Right. So next is the wavelength of the light used. The given lambda is equals to 589.3 nanometer, that is into 10 to the power of minus 9 meter. That is the wavelength used here. Next, the given the distance of the screen from the slit is 1.3, that is the given capital T, that is equals to 1.3 meter. So we know all these three values. So now substitute here and simplify. That is 3 into 589.3 into 10 to the power of minus 9, and the distance between the screen and the slit is given 1.3 whole divided by small d, that is the difference between the slits. Distance between the slits is 1.1 into 10 to the power of minus 3, that is in millimeter. So here we can shift one digit and here also we can shift one digit, then it becomes 3 into 589.3 into 13 divided by 11 into 10 to the power of minus 9. If we shift 10 to the power of minus 3 to the numerator, then it becomes plus 3. So minus 9 plus 3, it becomes 10 to the power of minus 6. Right? So now by using the calci, if we substitute the values 3 into 589.3 into 13 divided by 11, so we get the value is, by simplifying, that is 2089.3 into 10 to the power of minus 6. So if we shift 3 digits, then it becomes 2.089 into 10 to the power of minus 9 meter, or it becomes 2.809 nanometer. Otherwise we can write 2.089 nanometer. So this is the solution, that is x7 minus x4, the distance between the centers of the fourth and seventh bright fringe. So we need to subtract the seventh bright fringe with the fourth bright fringe. Then the solution is 2.089 nanometer. Right? So we have to remember this one. Xn is equals to n lambda d divided by d, where xn is the distance of the bright fringe from the central bright fringe. Right? So move on to the next question. So next, fifth question. Here in Young's double slit experiment, so in Young's double slit experiment, the two slits are 0.3 millimeter apart and are illuminated by a light of wavelength 650 nanometer. Calculate the distance of calculate the distance of first one, third dark fringe, in the second one, fifth bright fringe, from the midpoint from the midpoint in the interference pattern in the interference pattern obtained on the screen 1.2 meter away 1.2 meter away from the slits, right? So here in this question, here also the same experiment, Young's double slit experiment. Two slits are separated by distance 0.3 millimeter. Here is the 0.3 millimeter, that is small d, are illuminated by a light of wavelength 650 nanometer, that is lambda is equals to 650 nanometer. Next, we have to calculate the distance of third dark fringe and fifth bright fringe. So one we have to calculate is the dark fringe and another one we are going to calculate here is the bright fringe. From the midpoint in the interference pattern obtained on the screen, so the screen is 1.2 meter away from the slits, that is capital D they given from the slits, that is 1.2 meter. So here the midpoint means the central maximum, that is if we consider O is the central, so this one is the bright fringe. So from here we are going to find the first dark fringe, that is here we are going to calculate x3, that is the third dark fringe, and second we are going to calculate is fifth bright fringe, that is from center also. This is x5. So in the last problem we find that we know the formula for the bright fringe, that is xn is equals to n lambda d divided by d. So here for the dark fringe, that is for the third dark fringe, so here we get in the interference pattern alternating dark and bright patterns. So in the center we have bright fringe, right? So in the center we have the bright fringe. So after the bright fringe we have one dark. After that again we have one bright. So again we have one dark, right? So if xn, in the last problem we written xn is equals to n lambda d divided by d. So if xn represents the nth bright fringe, that is if it is the value of n is 1 means we have the first bright fringe is first bright fringe. So after that again we have one dark fringe. For that dark fringe we have to write that is xn plus 1, right? So if 1 is the bright fringe, then for the next pattern we have to write is alternate. So this one is the bright fringe and this one is the dark fringe. So if the position is 3 here, the third position we get the bright fringe, then after third, that is fourth, for the fourth position we are getting dark fringe, because we have alternate bright and dark. After the bright we need dark fringe. So after dark again here if you write means again after 4 we have 5, then it will be bright. So after that we have to write means here 6 is the dark. So alternate we have dark and bright. If xn is the bright fringe, then dark fringe is that is 3 plus 1. That's why we written n plus 1. Right? Understand this one? So this is for the bright fringe. Xn is equals to n lambda d divided by d. So this one is the central bright fringe. That's why we written xn value, that is n lambda d divided by d. For the dark fringe, after one bright fringe we need one dark fringe. That's why we are adding plus 1. Then we get the dark fringe. Next, xn plus 1, that is equals to, that is dark fringe nothing but the diffractive interference. The condition for the diffractive interference is n plus 1 by 2 into lambda d divided by small d. So this is the difference for the bright fringe and for the dark fringe, right? So here they asked for the third dark fringe. So for third we need x3, then we have to substitute the value of n. So first here we write this is for bright fringe and this is for the dark fringe, that is nth dark fringe. That is we get x of n plus 1 is equals to the condition for the dark fringe, that is diffractive interference, n plus 1 by 2 into lambda d divided by d. For the bright fringe we have constructive interference, that's why we are written in the RHS, that is n lambda d divided by d. So we need to find the first case, that is for the first case the given third dark fringe. So we need x3, that is third dark fringe, that is x3, and also the given the distance between the slits small d is equals to 0.3 millimeter, that can be written as 0.3 into 10 power minus 3 meter. Next, the wavelength of light lambda is equals to 650 nanometer, that can be written as minus 9 meter. 650 into 10 to the power of minus 9 meter. Next, capital D, that is distance from the screen to the slit, that is 1.2 meter, right? So this is for the first one. For x is equals to 3, that is here we need x3 already, we have 1 here, then we need to substitute the n value is 2, right? So for first one, that is we need n is equals to 2, then substitute in this formula, then it becomes 2 plus 1, that is equals to 2 plus 1 by 2. So the lambda value is 650 into 10 to the power of minus 9. The distance between the slits and the screen is 1.2 divided by small d, that is 0.3 into 10 to the power of minus 3. So here we take LCM and simplify. 4 plus 1, that is 5 divided by 2 into, so here 0.3, 1.2, that is 0.4. 0.4 into 650 into 10 to the power of minus 9, it's minus 3 goes to the numerator, it becomes plus 3, that is minus 3 that is minus 9 plus 3, that is equals to minus 6. So here 2 ones are 2 twos are, that is 0.2. So 5 twos are 10, that is 1, right? So 1 into 650, we getting 650 into 10 to the power of minus 6. Here it is x3, that is 2 plus 1, we get x3. So if we shift further 2 or 3 digits, then here it is 10 to the power of minus 6. Here we get 1.2 divided by 3, that is 4. Here it is not 0.1, it is 4. So here we get 2. That is 5 to the 10. Then here we get 1 more 0. 6,500. So if we shift the 3 digits, then we have to multiply. That is, we get 6.5 into 10 to the power of minus 9 meter. So 10 to the power of minus 9 can be written as 6.5 nanometer. So this is the third dark fringe, right? So if we directly substitute here, means we get the wrong answer. That's why we have to check for the dark fringe and for the bright fringe. So for always dark fringe, it is xn plus 1. That is, the first one is the bright fringe. That is for, because of the central we have bright fringe. After that, the next consecutive is the dark fringe. That's why we taken n plus 1, right? So this is for the dark fringe. X3 is equals to 6.5 nanometer. So move to the second case. That is, we need to find bright fringe. So for the bright fringe, for the second case, that is for the bright fringe, we have xn is equals to n lambda d divided by d. So here we need to find the n value is 5. That is fifth bright fringe. So n value is 5. 5 into 650 into 10 to the power of minus 9 into 1.2. That is, capital D is 1.2 divided by small d is 0.3 into 10 to the power of minus 3. So here 3 4s are 12. If we shift 12 divided by 3 becomes, so 3 4s are 12. So 4 into 5, that is 20. 20 into 650 into 10 to the power of minus 9 plus 3. So it becomes minus 6. So here 2 zeros. Next 2 5s are 10. 2 6s are 12 plus 1, 13. That is 13,000 into 10 to the power of minus 6. So if we shift 3 digits, means it becomes 13 into 10 to the power of minus 9. Then this can be written as 13 nanometer. So this is the x5. That is for fifth bright fringe, we get 13 nanometer. For all these, we need to remain this one, right? So anywhere they ask for the dark fringe, means we need x is equals to n plus 1. So if they ask for the third dark fringe, the n value becomes 2. If they ask the fifth dark fringe, then n value becomes 4. So one value we are taken, n value is lesser, right? So this is another method problem, right? Move to the next problem. So these are the questions which they asked in the previous year question paper based on this concept. So simple problems are there. We have to understand the question properly. What the question is they are asking and what we are going to find based on only one formula, that is fringe width. Beta is equals to lambda d divided by d, and if they ask the distance from the central bright fringe, then it becomes xn for the bright fringe it is xn is equals to n lambda d divided by d, and it's for the dark fringe means xn plus 1 is equals to n plus 1 by 2 into lambda d divided by d, right? For this year, the possibility of the problem may come from this chapter, because this year they asked the problem from ray optics. So possibility of coming problem from this chapter. So next, sixth question, say in Young's double slit experiment, the slits are separated by the slits are separated by 0.28 millimeter, and the screen is placed at a distance of 1.4 meter away 1.4 meter away from the slits, right? The distance between central bright fringe and fifth dark fringe is measured to be 1.35 centimeter. Calculate the wavelength of light used. Full stop. Also find the fringe width. If the screen is moved, 0.4 meter towards the slits, for the same experimental setup. So here we need to calculate, or we need to find two questions. So here they given same experiment, Young's double slit experiment. The given is the slits are separated 0.28 millimeter, and the distance of the screen is at a distance of 1.4 meter away from the slits. That is, here they given small d, and here it is capital D, and the distance between the central bright fringe and the fifth dark fringe is measured to be 1.35 centimeter. Then calculate the wavelength of light used. We need to find the wavelength of light used, and also find the fringe width if the screen is moved. So this is the second part, that is, if we move the screen towards the 0.4 meter towards the slit, then we need to find the fringe width, that is beta, right? So here they are given what they are given. So first we write here what they are given and what we need to find. So here they given small d, that is 0.28 millimeter, that is into 10 to the power of minus 3 meter. Next, the given capital D is equals to 1.4 meter. Next, the distance between the central bright fringe and fifth dark fringe, that is the given the distance of x5, that is x5 is equals to 1.35 centimeter, that can be written as 1.35 into 10 to the power of minus 2 meter. So from this we need to find the wavelength of light used. So first we find the lambda, then we move on to the next part. So if we consider here, this one is the screen and here is the central bright fringe. So from here to here we have one dark fringe, that is this one is the fifth dark fringe. So we can write x5, that the given the distance from central bright fringe to the fifth dark fringe, the given the distance is how much? That is 1.35 centimeter. And also they given the slit distance and also the distance between the screen and the slit. So here they given we have for dark fringe, we have the formula for the dark fringe. In the last problem we discussed, that is x n plus 1 is equals to n plus 1 by 2 into lambda d divided by small d. Right? So this is the formula for the dark fringe. So here they given fifth dark fringe, that means the n value becomes 4. For fifth dark fringe the n value becomes 4, that is 4 plus 1 we get 5. So all the remainings here they given d and here it is small d, and also they given x5 distance from the central, that is how much? 1.35. So if we write here, then it becomes x4 plus 1, that is equals to 5. Here the value of n is 4 plus 1 by 2. Here we need to find the lambda, keep as it is lambda into the distance from the slit to the screen, that is 1.4 meter divided by the distance between the slits, 0.28 into 10 to the power of minus 3. So here the xy value is also given, how much? That is 1.35 into 10 to the power of minus 2, right? That is equals to, if we take LCM then it becomes 8 plus 1, that is 9 by 2 into, so 1.4 lambda divided by 0.28 into 10 to the power of minus 3. So we need lambda, then keep lambda as it is, it shifts to the LHS, then it becomes 1.35 into 10 to the power of minus 2 into 2 into this one also, if we shift to the LHS it becomes 0.28 into 10 to the power of minus 3 whole divided by, we kept 9 into 1.4, right? So if we simplify by using calculator, then here we get 2, that when 14 can be written as 0.7. 2 divides 1.4, that we get 0.7. So if we further simplify by using calculus, then we get the value lambda is equals to, that is how much means 0.06. So if we simplify all these values, we get 0.06 into 10 to the power of minus 2 into 10 to the power of minus 3. We can write 10 to the power of minus 5. So if we shift this digit to left, that is 102030 6. Here it is minus 3. That is how much it becomes? That is 20 minus 7. Further we need 2 zeros means 600 into 10 to the power of minus 9 meter. That is, the wavelength of light is equals to lambda is equals to 600 into 10 power minus 9 meter. That can be written as 600 nanometer. So if you calculate this value by using the calculator, we get 0.06 into 10 to the power of minus 5. So we are shifting the 6 by 4 digits. That's why into 10 to the power of 4, that is minus 4, 10 to the power of minus 4, 10 to the power of minus 5, we get 10 to the power of minus 9. So minus 9 can be written as 600 nanometer. So this one is the first part. By using this condition, we find the wavelength of light used, that is 600 nanometer. So in the second condition, what they are given? So initially it is the slit, right? So here is the screen. That is, in the given question, here the distance is 0.28 millimeter and the distance between the slit and the screen is how much from here to here is 1.4 meter. So in the second part, they are telling that the screen is moved 0.4 meter towards the slit. That is, towards means towards the left side. Away means it is away, that is towards the right side. So this screen is moved how much means? So from here to here, we move the screen by 0.4 meter. So that is 1.4 meter minus 0.4 meter. Then we get the distance between the slit and the screen for the second case. That is 1.4 minus d is equals to 1.4 minus 0.4. That is d is equals to 1 meter. So understand this one. They are telling this screen is moved towards the slit. So this one is the slit. The screen is moving towards the, that is moved towards the slit by the distance 0.4. Then the final distance between the slit and the screen is 1 meter. So here there is no change. That's why d becomes 0.28 into 10 to the power of minus 3 meter, right? So here same experimental, from here some source of light we use, we find that one, that is 600 nanometer. The we find in the previous case, that is 600 nanometer wavelength. Then we need to find the fringe width beta. That is same experimental setup. Here we are not changing any source for the second case. Hence we are taken the source of the light. The wavelength is 600 nanometer, and we need to find the fringe width. So we have the formula for the fringe width. That is beta is equals to lambda d divided by d. So we need to find the beta. Then beta is equals to lambda is 600 nanometer into 10 to the power of minus 9. The distance d is 1 and the d small d is 0.28 into 10 to the power of minus 3 meter. That is millimeter. We are written millimeter into meter. So what happens here is 600 divided by 0.28 into 10 to the power of minus 6. So the fringe width 600 divided by 28. So how much that is? If we simplify by using the calc, we get, here it is, beta is equals to 2000. The value is 600 divided by 0.28. 2142, that is 2142 into 10 to the power of minus 6. So if we shift 3 digits means that is divided by 1000 means we get 2.14 into 10 to the power of minus 3 meter. That is the fringe width is 2.14 millimeter. So this one is the final answer, right? So here we have two cases. One case we find the wavelength of light used, and in the second case we find the fringe width when the screen is moved towards the slit. That is beta is equals to 2.14 millimeter. So the last problem of this topic, that is seventh problem. Say a beam of light consisting of two wavelengths 650 nanometer and 520 nanometer is used to obtain interference fringe in Young's double slit experiment. In Young's double slit experiment, what is the least distance? What is the least distance from the central maximum, from the central maximum where the bright fringes due to both wavelength coincide here given D is equals to 2 millimeter and capital D is equals to 1.2 meter. So here a beam of light consisting of two wavelengths. The light which coming from the slits have two wavelengths, that is 650 nanometer and 520 nanometer, is used to obtain the interference fringe in Young's double slit experiment. So what is the least distance from the central maximum where the bright fringe due to both the wavelengths coincide? That is, if we have the screen, then here we have two wavelengths, that is two lights which are coming from the slits. So if the position of, that is, if we consider for this one, we need one position, that is for this wavelength, if it coincides somewhere here and this one somewhere here, then we need to find which is the, that is from the central maximum, this is the central maximum from here, where the bright fringes due to both wavelength coincide. That is, if we take them individually, they are separate, they form separate fringes. So when these two lights are coming, these two fringes are coincide at somewhere on the screen. So we need to find, so at what distance from it is, that is coinciding, that is at the least distance. We get, here is the bright fringe, again dark, bright, dark. So in this we need to find least distance, that is which one is the nearer to the central maximum, that is which bright fringe is nearer to the central maximum. For that distance we need to calculate bright fringes, that is the least distance. We need to find which one is the least distance, right? For that we have taken the position of, when two wavelengths are coinciding, then their positions becomes equal. So here x1 is the bright fringe for the first wavelength and x2 is the bright fringe for the second wavelength. If these two are coinciding, means these two are meeting at one point, means this value is equals to this value, right? So x1 value is equals to x2 value. So if we write the formula for the bright fringe, x is equals to n lambda d divided by small d. So this one, for we taken, we have two wavelengths, then this is for x1 becomes n1 lambda 1, the distance between the screen and the slit is same and the distance between the slits is same, hence these two are constant, then x1 becomes n1 lambda 1 d divided by small d. This is for the second wavelength, then x2 is equals to n2 lambda 2 d divided by d. So this is for the first wavelength and this is for the second wavelength. So we have these two values and these two are for the bright fringes. Then we substitute here, we get n1 lambda 1 d divided by d is equals to n2 lambda 2 d divided by d. So in the LHS and RHS we have the same terms, then we can cancel these two terms, right? So remaining is n1 lambda 1 is equals to n2 lambda 2. So if we take on the ratio n1 by n2 is equals to lambda 2 divided by lambda 1. So here we have taken this one as lambda 2 and here is the lambda 1, that is the value of lambda 2 is 520 nanometer, both are in nanometers, then we can directly take nanometers, that one will be cancelled. 520 divided by 650 into 10 to the power of minus 9. So 10 to the power of minus 9, 10 to the power of minus 9 cancels, then 13, so 0 0 cancel. So here 13 5 is 65 and 13 4 is 52. That is n1 by n2 is equals to 4 divided by 5. So here the n1 is the position, that is the position of the first wavelength, that is 4, and n2 is the position that is for fifth. So here these two are coinciding. So 4 is the least or 5th is the least. So here the least one is the 4th. That's why we are taken n is equals to 4. The least distance we are going to calculate fourth position. That is, here we get n1 is equals to 4, n2 is equals to 5. So if we observe, n1 is the position, that is 4 from the central band and 5 is the position from the central band. So 4 is nearer to the central band. That's why we are taken the wavelength of first one, that is lambda 1. That's why x is equals to n lambda d divided by d. n1 lambda 1. So here we are taking the value of n1, that is 4. That is 4 into lambda 1 value is 650 into 10 to the power of minus 9, and the given d value is 1.2, and they also given small d value 2 millimeter, 2 into 10 to the power of minus 3. So here we can write 2 to the 4, then 2.4, 2 into 1.2 is 2.4 into 650 into 10 to the power of minus 9 minus 3, that becomes minus 6. So if we multiply 2.4 into 650, we get 1560, that is 1560 into 10 to the power of minus 6. So if we shift, that is divided by 1000, then it becomes 1.5 into 10 to the power of minus 3 meter, or we can write 1.5 millimeter. So at this distance, that is from 1.55 millimeter from the central bright fringe, the two wavelengths are getting coinciding, right? So this is the solution, that is the condition for two bright fringes, that is of the two wavelengths are getting coincide, means x1 is equals to x2. For the bright fringes they given, that's why we taken n lambda t divided by d. So here one represents suffix, that is x1, x2. Otherwise we can take x, x dash, right? So once they ask this problem for the examination. So this is about the problems based on the Young's double slit experiment. So in the next class we will start with the new topic, that is diffraction. Thank you.